Welcome to the second lecture of our course on high performance computing. In the first lecture we had seen something about programs, what a program is, how a program may have to be translated for execution on a digital computer, and we then moved on to a discussion of how data is represented. We had seen that there are different kinds of data and that character data is represented using a standard convention called the ASCII code. The ASCII code is ASCII is a short form for the American Standard Code for Information Interchange, and it is an international standard. We then moved on to how the integer data is represented. We recall that integers are whole numbers, that is numbers without fractional parts. And I mentioned that from your C programming you are familiar with the concept of both signed and unsigned integers. It therefore stands to reason that in computer systems there must be different possibilities for how to represent values that are signed as opposed to those which are unsigned. So I went into one of the possibilities of how to represent signed integer data, which is the sign magnitude representation. Remember that what we are trying to understand here is a scheme that could be used in a digital computer to represent a variable which could take on either negative or positive integer values. Now here the key thing to understand is that the sign must be included in the representation. So if I have an n-bit representation for a signed integer value, then clearly the sign must be incorporated in that representation. In the sign magnitude representation, the most significant bit of a signed integer is used as a sign bit. In other words, the most significant bit indicates whether the signed integer is a negative or a positive value. The remaining bits indicate the magnitude of the value in binary, as this summation on the right of this expression would have you understand. And therefore the bit at the left, or bit xn minus 1, is the sign bit in the sign magnitude representation. And as a standard convention, as I had mentioned last time, we refer to the bit which contributes the least to the magnitude of the value that is being represented as the least significant bit. And in this case I am showing the least significant bit on the extreme right and numbering it as x0. Please note that this is just a convention. I could just as well have shown the least significant bit on the extreme left, and the expression would have been exactly the same, because I would have labeled the bit at the extreme left as x sub 0. Okay, so this is one way that signed integers can be represented. I had mentioned at the end of the previous lecture that this is in fact not the most popular way among computer manufacturers for representing signed integers. But let's just look at some examples to make sure we understand this. Okay, now let's suppose that I'm representing signed integers in 8 bits. In other words, I have x0, x1, x2, x3 up to x7. Right? So xn minus 1 is x7. The question is how would I represent 13 plus 13? Plus 13 is a signed integer with a positive sign. The answer is very clearly the most significant bit, or the sign bit, is going to be a 0, because the value has to be positive. 13 is a positive value, and therefore minus 1 must be raised to the value 0. So the most significant bit must be a 0, which it is, and the remaining bits must be such that this summation adds up to the value 13. So I notice here that there is 1 multiplied by 2 to the power of 0, which is 1, plus 1 multiplied by 2 to the power of 2, which is 4, plus 1 multiplied by 2 to the power of 3, which is 8. So the value that's being represented is 8 plus 4 plus 1, which is 13. So the sign magnitude representation for plus 13 is 0, 0, 0, etc., 1, 1, 0, 1. Similarly, the sign magnitude representation for minus 13 is going to be very similar, except that the sign bit is going to be a 1. Okay. Now, if sign magnitude is not the most popular representation for signed integers, you ask, what is? And the answer is something called the 2's complement representation. Okay, now in the 2's complement representation, the n-bit value xn minus 1, xn minus through x0 represents the signed integer value as shown by the expression over here. Now if you look at this expression carefully, you'll notice that the second term is exactly the same as the second term for the sign magnitude representation. I'll just look at this term. It's summation from I equals 0 through n minus 2, x sub I 2 to the power of I. I'm going to go back to the previous slide so that you can just confirm that this is the same as this term over here. Right? It's exactly the same. So the only difference between the sign magnitude representation and the 2's complement representation comes in the first term. In the case of the sign magnitude representation, the first term was minus 1 to the power n minus 1. Minus 1 to the power x sub n minus 1. And that was going to be minus 1 if x n minus 1 was 1 and plus 1 if x n minus 1 was 0. In the 2's complement representation, on the other hand, we have a magnitude associated with the sign bit. And the magnitude is going to be quite high. In other words, if the most significant bit that we see over here is a 0, then this is going to be x n minus 1 multiplied by 2 to the power n minus 1. So it's going to have a positive value of great magnitude. And if it's a 1, then this is going to have a negative value of a great magnitude. So the net effect is that, for example, if I wanted to represent in 8 bits plus 13, the value would be similar to what we saw in the sign magnitude representation. X n minus 1 is 0, therefore this term is effectively 0, and the magnitude is the same that as we had in the case of the sign magnitude representation. Whereas if I want to represent minus 13, I do need to have a large negative component, because the remaining, the second term is going to add a positive value to the net result of this value. Therefore, a large negative value added to a smaller positive value, which is going to result in minus 13. Now let's just verify that this is in fact the same as minus 13. I've just put it up, and we need to verify that this is equal to minus 13 if this expression is what is used in the representation. So how do I compute what this corresponds to? I note that this representation includes 1, so minus x n minus 1 is 1 multiplied by 2 to the power n minus 1, which is 2 to the power of 7. 2 to the power of 7 is 128, so it's minus 128. That's followed by a 1, which is part of this summation, which is going to be 2 to the power of 6 in an 8-bit representation. So that is 64, and so on. So the net result is that in evaluating this using this expression, I find out that it's equal to minus 128 plus 64 plus 32 plus 16. Then there's no 8 and there's no 4, but there is a 2 and there is a 1. And when I add this up, what I get is minus 13. So this is an equivalent way to represent signed integers. Now the property that we see over here is that if the value that is being represented is negative, then most definitely the most significant bit, the bit at the extreme left, is going to be a 1, because that's the only way that the sum based on this expression could be negative. Therefore, in some sense, the most significant bit is a sign bit, but it is not only a sign bit, because it also has a value associated with it. It is a highly significant bit in that sense, and therefore we don't refer to it as a sign bit, but as the most significant bit. So that's the way in which the 2's complement representation and the sign magnitude representation differ from each other. Now the question that you'll ask, and we'll answer a little bit later, is why is this better than the sign magnitude representation? But let's look at an example first. Okay, now in this example, we're going to try to understand what it means to be in the 2's complement representation. So here what I've given you is a 2's complement representation for a value. We don't know what the value is. We know that it's a signed integer value. I'm telling you that it's a 16-bit 2's complement value 0xED7E. Now this, when you look at it, you probably don't recognize this as being a number. So I do need to explain what I mean by 0xED7E. Let me start by doing that. Now the 0x is an indication to you that the binary value which is being presented to you is being shown in something called the hexadecimal notation. So 0x is just a prefix telling you that the subsequent value is actually a hexadecimal representation. Hexadecimal means base 16. So up to now we were talking about base 2. Binary values are represented in base 2. Here we're hearing about a number which is represented in base 16. So we do need to understand what's happening here. Also, what is this E, D, 7 and E? So let's just consider this 16-bit binary sequence, 1, 1, 0, etc., etc. So there are 16 bits here. Now, I know that if I was to view this as a binary value, and normally if this was a unsigned binary value, I would say that this has a value of 0. This bit, the one on the extreme right side, has a value of 2, a value of 4, and so on. But if I was to group these bits into groups of 4 starting from the right side, bearing in mind that 2 to the power of 4 is equal to 16, I would actually find out that the bits in any one of these groups, for example, consider the bits in the rightmost group. There are 4 bits there. Now, those 4 bits currently have, in this particular example, those 4 bits have the value 1, 1, 1, 0. But in general, a sequence of 4 bits could take on 16 different values, from 0, 0, 0, 0 to 0, 0, 0, 1 to 0, 0, 1, 0, all the way up to 1, 1, 1, 1. So there are 16 different values that a group of 4 bits could take on. And these are in fact the 16 possible values of the hexadecimal base 16 number system. So what we've done over here is, rather than representing huge binary strings such as the 16-bit binary string by 16 bits, which will take a long time to read or to write, I'm using a shorter notation in which I compress a bit sequence into a hexadecimal sequence by just grouping the bits from the right in groups of 4. And then I read each of those groups of 4 as the equivalent hexadecimal digit. Now, the question you will ask is, what are the hexadecimal digits? I know that in the decimal system, the decimal digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In the hexadecimal system, there are 16 digits. And I can use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 as the first 10 of those digits, but I need 6 more. And therefore, the convention that is used is that we use A, B, C, D, E, and F to represent the next 6 hexadecimal digits. Therefore, the 16 hexadecimal digits are 0 through 9, followed by A, B, C, D, E, and F. In other words, the binary value 1, 1, 1, 1, which corresponds to the value 15, would be associated with the hexadecimal digit F. Similarly, the binary value 1, 0, 1, 0, which corresponds to 10, would be associated with the hexadecimal digit A. So when we read this, we might say 0 through 9, A which is 10, B which is 11, C which is 12, D which is 13, E which is 14, and F which is 15. So the hexadecimal notation here, it's indicated by the fact that I prefix the value by 0x, and the remaining are digits from the hexadecimal number system. In other words, values between 0 and 9, or A through F. Okay, so we're going to represent values typically in the examples that are to come using this hexadecimal notation. So this particular value that I have, if I was to read it off, 1110 is E, 1101 is D, 0111 is 7, 1110 once again is E. And therefore, this 0xED7E that I had over here actually corresponds to this sequence of bits. Okay. Now, the question that we had started with was, what is the 16-bit 2's complement value 0xED7E? Ultimately, this is the 2's complement representation for some signed integer. And I want to know in decimal what that signed integer value is. Right? So the way that I can get an answer to that question is using this expression. Just as we did in this example, I can do the same thing with this example once I understand the meaning of the hexadecimal notation. Okay, now I had given you some indication that the 2's complement representation is considered superior to the sign magnitude representation, and it might be useful for us to understand on what grounds that opinion has arisen. Now, what are the different considerations that might come into play in deciding whether one representation for signed integers is better than another? The answer is, ultimately, as you will understand, somebody will have to build an electronic circuit to add signed integer values. This is what is going to be present in a computer in order to execute the add instruction that your program might make use of. So the speed of the arithmetic might be an important consideration in deciding whether one representation is better than another. Another consideration which might come into play is the speed of comparison. How quickly can a circuit determine whether whether one value is greater than another value or less than the other value. So this is another operation for which a circuit might have to be built, and therefore the speed of that circuit might be critical in determining which of these representations is better for the execution of programs. Another indication, another factor that might come into play in deciding which representation is better than another is the range of values that can be represented. Okay, now just to give you a little bit of idea about this, if you think about the sign magnitude representation and ask yourself, what is the representation for the value 0? You will quickly realize that there are actually two representations for the value 0. One representation will have a sign bit of 0 followed by all zeros. The other representation will have a value of 1 followed by all zeros. Technically that stands for -0, but that is the same as 0. Therefore, in the sign magnitude representation, there are two representations for the value 0. Now, if I have let's say a 4-bit sign magnitude value, I know that there are only 16 different possible values that can be represented from 0, 0, 0, 0 up through 1, 1, 1, 1. If I am using two of those values for 0, that means that only 14 other values can be represented using the sign magnitude representation in 4 bits. On the other hand, if I have 4 bits in the 2's complement representation, I can represent 15 other values in addition to 0. Therefore, the range of values that can be represented is larger in the case of the 2's complement representation. As it happens, the speed of arithmetic and comparison is also superior, for which reason the 2's complement representation has become the more popular of the two that we have seen. Right, so the 2's complement representation is very widely used in digital computers for the representation of signed integers. Okay. Now with this we have seen that character data is represented almost universally using the ASCII code, and that signed integer data is represented most widely using the 2's complement representation. What other kinds of data do we have to take into account? Now I'm going to talk about something called real data. All of you have encountered real data, and you know that a real number is usually defined with reference to the real number line. You have a picture of an infinitely long real number line which extends infinitely from your left to your right, with in the middle somewhere the value 0, and you know that a real value is basically a real number is any point on that line. And you also know that between any 2 points on the real number line there are an infinite number of other points, and therefore an infinite number of other real numbers. So these are the properties of real data. So there are infinitely many points between any 2 points on the real number line. And you're all familiar with the real world phenomenon which must be modeled as real numbers. And this is something which I didn't talk about in connection with signed or unsigned integers, but it's something to think about. In writing a computer program, you have to make a decision. You're writing a computer program to achieve some well-stated objective. In deciding whether to declare a variable as an integer variable as signed or unsigned, you would have to know whether there's a possibility that the real world phenomenon corresponding to it could take on negative values, in which case you would declare it as an unsigned piece of data, unsigned integer. Similarly, you must be aware of situations where the real world phenomenon that you're trying to take into account in your computer program may have to be modeled as a real value. Okay, now unfortunately in computer systems it is not possible to represent all real values exactly, because as we saw there are an infinite number of real values between any 2 real values, however close they are on the real number line. And therefore different kinds of representations must be used to approximately represent many real values. And one such representation is something called the floating point representation. And it is from the name of this representation that the keyword float in the C programming language comes. You declare a variable called float x. You are declaring it to be a floating point variable, and essentially you are saying that the x corresponds to some real value. Okay, now among the different floating point representation possibilities, the most widely used international standard is something called the IEEE floating point standard. and one of the IEEE floating point standards that I'm going to talk about is known as the IEEE 754 standard. Okay, now the situation as far as real values is concerned is that, like signed integers, real values could be either positive or negative. The real number line stretches infinitely to your left and to your right. Half of it is negative, it corresponds to negative values, the other half of it corresponds to positive values. In addition, in the IEEE, therefore there is the need for a sign bit, which is the first part of the 32-bit IEEE floating point representation for a real piece of data. To represent the magnitude of the floating point of the real value, it's not possible to use something like the magnitude representation used for signed integers, because real values could become much larger or much smaller than what the whole numbers that we were concerned with as far as integers are concerned. Therefore, the convention that's used in the floating point representations is that we have something called an exponent and something called a fraction, and put together the sign, the exponent and the fraction represent a real value. The way that the exponent is used is that it is used as the power of some kind of a base, and the way that the fraction is used is that it is used as a fractional part which is multiplied by the base raised to the power of the exponent. Now, in the IEEE 754 standard, the somewhat interesting expression is used to interpret the value of a 32-bit float value. The sign bit is not too difficult to understand. If the sign bit is a 0, that means that the overall real value is positive, whereas if the sign bit is a 1, the overall real value is a negative real value. Next, we have the fraction part, which is in this construct 1.f. So the fraction part is a 23-bit fraction, a sequence of 23 zeros or ones, and 1.f defines the, in some sense, the magnitude of the value. Then the exponent part, minus 127, is what the power 2 is, the power to which the constant 2 is raised in order to give the multiplicative factor through which this real value will be evaluated. So we do need to understand a few things about this representation. First of all, why do they use this 1.f, and secondly, why don't they just raise 2 to the power e instead of having 2 raised to the power e minus 127? And I'll talk about this, but first let's look at an example. So this expression, we want to find out how is the value, the decimal value 0.5 represented. What I mean by the decimal value 0.5 is what you understand in day-to-day language as half. Decimal means base 10. Okay, so in order to evaluate 0.5 in the IEEE floating point representation, I need to get it into this kind of a form. Minus 1 to the power s multiplied by 1.f into 2 to the power e minus 127. Therefore, first of all, I need to represent this value in binary. So how do I represent 0.f in binary? The answer is, just as in the decimal system I can have a binary point, and just as in the decimal system I can have a continuation of the digits which were on the left onto the right. Remember that in the decimal number system I have a situation where the first digit is multiplied by 10 to the power 0, the second digit is multiplied by 10 to the power 1, the third digit by 10 to the power 2, and so on. Similarly, to the right of the decimal point, the first digit is multiplied by 10 to the power of minus 1, or divided by 10, which is why the value of 0.5 is 5 multiplied by 10 to the power of minus 1, which is equal to 5 divided by 10, which is equal to half. I can have a similar convention in the binary system, in which the first digit to the right of the binary point is actually multiplied by 2 to the power of minus 1, not 10 to the power of minus 1 as it was in the decimal system, but 2 to the power of minus 1, since this is the binary system. Therefore, if I wanted to evaluate half, I would have to have 1 multiplied by 2 to the power of minus 1, which is 1 divided by 2, which is half. Therefore, in binary, what I refer to as 0.5 in decimal, which I think of as half, is actually represented in binary as 0.1. Right? 1 is the binary point, 1 is the bit to the right of the binary point, which is therefore multiplied by 2 to the power minus 1. Okay, so half is equal to 0.1 in binary. This is still not in the form that I am looking for. I am looking for something in the form minus 1 to the power s 1 point fraction multiplied by 2 to the power of e minus 127. So I need to understand what s, e and f might be for this binary value. So I noticed that I can write 0.1 as 1.0 multiplied by 2 to the power of minus 1. So what I've done is, I know that in the IEEE floating point standard I need to have a 1 to the right, to the left of the binary point. Therefore I multiply this value 0.1 by 2. In other words, I shift the binary point to the right, and to compensate for that I multiply it by an additional term of 2 to the power minus 1. And you can readily see that 0.1 binary is the same as 1.0 into 2 to the power minus 1. Okay, so this is getting closer to the form that I want. In fact, I can now read off the IEEE floating point values for s, e and f from this directly. I'll notice that s, this is the IEEE floating point representation. So s is obviously going to be equal to 0. This is a positive value. I'll also notice that f is going to be a lot of zeros, because I have 1.0 and I want that to correspond to 1 point f. And I can also read off that e is going to be equal to 126, so that e minus 127 is equal to minus 1. So 126 minus 127 is equal to minus 1. Therefore I know that s is 0, e is 126 and f is a lot of zeros. Why am I showing a lot of zeros here? Because I know that in the IEEE floating point representation the f field contains 23 zeros. So the f field must have 23 zeros in it. Okay, now I now know what half looks like in the IEEE 754 representation. All I have to do now is I take the s and make it the most significant bit. I take the value of e and write it as the next 8 bits. So this is 126 in binary, and then I take the 23 f bits and put them at the end, and this 32-bit value is the IEEE floating point representation for half. It is the exact IEEE floating point representation for half. Okay, now there will be many real values for which there is not an exact IEEE equivalent, and therefore what is done in the IEEE standard is to approximate a real value which cannot be represented exactly by its nearest equivalent. Okay, let's just look at one more example. This will also help us to get a better understanding of the hexadecimal digits. So what I'm going to do in this example is, I'm showing you a value which has been represented in the IEEE floating point representation. I'm showing it to you in hexadecimal. Remember, 0x prefix lets you know that what follows is in hexadecimal, and this hexadecimal number is B, D, C, 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 C. Remember that B, D and C are all hexadecimal digits. A is the hexadecimal digit corresponding to 10, B is 11, C is 12, D is 13. Hexadecimal is the base 16 number system. So this is a 32-bit value. How do I know that it's 32 bits? Remember that each of these hexadecimal digits actually corresponds to 4 bits, right? And there are 8 of them, therefore this is a 32-bit value. Okay, now how do I evaluate this IEEE value, IEEE floating point value in terms of a number that I can understand? The answer is, I need to find out what is the value of s, what is the value of e, and what is the value of f. So I need to break this up into its components, and for that I'll need ready reference to the hexadecimal table. Remember that B, as I said, corresponds to 1010 or 10, C corresponds to 1011, etc. So it's useful to have this table in front of you until you become really familiar with the hexadecimal notation. So what do I do in order to expand this? I take the B and I replace it by 0, 1, etc. So I get 1011 for B, then I get 1101 for that D, and for each of the C's I get a 1100. So these are the 32 bits. Now once I've expanded the 32-bit value from hex into binary, I can now read off the sign bit, the bits corresponding to the exponent, and the bits corresponding to the fraction. The most significant bit is the sign bit, which is a 1. The next 8 bits are the exponent field, and the remaining 23 bits are the fraction field. So I read this off as a sign bit of 1, which means this is a negative value. I can now read the 8 exponent bits. I find out that the value, and I evaluate that in binary, I find out that it is the value 123. I bear in mind that in the IEEE representation 2 is raised to the power e minus 127. Therefore, I will quickly remember that the exponent value is actually going to be 123 minus 127 or minus 4. In other words, in the value I am going to have 2 to the power minus 4. I then have to read out the fraction bits. So I put a 1 in front of it. Remember that it is 1 point f, and I interpret the value as minus 1 point, the fraction bits 100, 1100, etc., multiplied by 2 to the power of minus 4. And I could evaluate this, and if I evaluated it, I would find out that it was equal to minus approximately equal to minus 0.1 decimal. Therefore, this IEEE floating point value corresponds approximately to minus 0.1. It does not correspond exactly to minus 0.1, but it is the closest IEEE value to minus 0.1. And therefore, if you have a program which sets a variable to minus 0.1 and then you looked at that particular variable in its binary form, you would probably find this as being the representation. Okay. So I am suggesting to you that it is possible for you to look at the IEEE floating point representation of a value inside a program of yours. And if you think about this a little bit, it may not be that difficult. Let's suppose that you have a program in which you have a variable declared as a float, which means that it's going to be represented using the IEEE single precision floating point representation. So I have a variable called float of x. So in the program, I could actually print out the value of x in hexadecimal form. And if I printed out the value of x in hexadecimal form, I would possibly find out that it looks something like this. Right? So there may be ways to write programs in which you can examine the binary representation of a float, and that you could write programs to do this. By the same token, it's conceivable that you could write programs to look at the representation of a signed integer variable, or to look at the representation of a character variable, and check whether what I told you about the ASCII code and the 2's complement code and the IEEE single precision are all correct. Right? So one can actually think about a lot of what I am talking about as things that can be experimentally verified on the computers that you have access to. And in general, one should think about high performance computing as being an extremely experimental discipline. Most things are going to be studied by writing programs. A lot of things can be learned, experimented with, or confirmed by writing programs and running them on the computers that you have access to. Okay, now I had actually asked along the way about a few of the oddities of this representation. For example, the exponent is represented in a very strange way. Remember, the exponent in the IEEE standard was represented in a form such that you had to subtract 127 from it in order to get the actual value of the exponent. In this particular example, the value of the exponent was minus 4. In other words, the exponent was a negative value. And I represented it by the value e equal to 123. So this gives us some hint as to why the IEEE designers of the IEEE floating point representation may have used this very strange notation for the exponent. The first thing to bear in mind is that in general, for floating point, to represent real values, the exponent would have to be a signed integer. Okay? For very small values, the exponent is going to be negative. For very large values, the exponent is going to be positive. Therefore, in general, the exponent value is going to be a signed integer. Now, it would have been possible to represent the exponent value using a 2's complement representation or the sign magnitude representation. But the designers of the IEEE standard chose to use something different. They used something called the excess 127 representation. The representation that we saw, where the value 4 is represented by 123, because 123 minus 127 is equal to minus 4, is known as the excess 127 representation, and that is what is used for the exponent in the IEEE standard. Okay? So the question is, why do they use the excess 127 representation instead of using something else? And the answer is that in the excess 127 representation, it is much easier to compare values. Right? It is easier to determine whether one value is positive and one value is negative, and to compare values than with sign magnitude representation or the 2's complement representation. The other interesting question which arose was, why do they use that very strange representation for the fractional part, where they have 23 bits of value inside the representation, but then they assume that there is a 1 point f. And that is what is known as the normalized representation. Now, the reason for the normalized representation is, let's suppose that they didn't have the idea of 1 point f minus 1 to the s multiplied by 1 point f multiplied by 2 to the power e minus 127, but instead they had used 0 point f. Now, if they had used 0 point f, just note that inside the fractional field of 23 bits, it is possible that the first bit could have been a 0, or the first 5 bits could have been zeros. Okay? What this means is that there would have been many different ways to represent the same real value. I could have represented the real value half as 0.1 into 2 to the power of 0, or I could have represented the value half as 0.01 into 2 to the power of 1, or I could have represented it as 0.001 into 2 to the power of 2, and so on. So there would have been many different possible ways to represent the same real value. What this would have meant is that there would have been many less values that could be represented using the floating point representation. So to overcome these problems, they use this normalized representation where they have 1 point f, so that there is only one way to represent the value half, as 1.000 multiplied by 2 to the power of minus 1, and so on. Therefore, the normalized representation is used to provide a unique representation, and that is why we have 1 point f and not 0 point f. Just for your additional information, I would like to mention that there are some other features of the floating point, IEEE floating point representation, which might be of interest to you, and they are known as the special forms. Now, some of the special forms may actually have become clear to you if you think a little bit about, for example, how could you represent 0 in the IEEE floating point representation. Now, there is a problem in representing 0 in the IEEE floating point representation. Let me just go back a little bit. Just think about representing 0 in the IEEE floating point representation. Now, I can represent plus 0 by making the sign bit equal to 0, but there is no way for me to prevent this 1 point from creating some magnitude as far as the value is concerned. And therefore, there is in fact no way to represent 0 precisely using this expression. That is one of the problems with the IEEE floating point representation, which has to be overcome by a special form. In other words, 0 must be treated as a special case. 0 is not representable exactly using the expression that we had. You should recall that we might represent 0 approximately by a very small value. But typically in computations that we do, it might be important to represent at least 0 exactly, which is why 0 might have to be treated as a special case. And there are a few other special cases which the designers of the IEEE standard have included. One of these special cases is something known as the denormalized values. And basically the denormalized values are a special case through which one can represent extremely small values. The other special case that is allowed is the representation of 0. And 0 is represented by using an exponent value of 0 and a fractional value of 0, along with a sign bit of either 0 or 1. So you can represent both plus 0 as well as minus 0. An additional special case which is taken into account is a precise representation of infinity. So if the exponent field has a value of 255, decimal 255, and the fractional field has a value of 0, that corresponds to the value infinity. So you can represent both plus infinity and minus infinity by using the appropriate sign bit. There is also a representation for something called not a number, which is written as NaN, and this is a value which may result from certain types of computation. For example, if you have a computation in which you divide 1 by 0, floating point 1 by floating point 0, then technically one may not want to view this as a meaningful value and describe it as something which is not a number. Therefore, in hardware which is built using the IEEE floating point standard, such a computation may result in a value which is called not a number, which has an explicit representation for it. Now, as far as these special forms are concerned, you should note that the IEEE standard defines not only ways to represent these special case values, but also for arithmetic to happen on these special case values. So, for example, if I have a floating point variable called x and a floating point variable called y, and during the execution of my program, x takes on a value which happens to be infinity, and I have an expression in my program which adds x to y. It would be useful if my program is not forced to halt because of an error, but rather is allowed to continue to execute, because the meaning of x plus y is contained inside the floating point representation. For example, if it is understood that infinity plus a normalized value is actually infinity, and that the hardware will do this computation, then it is possible for programs which generate not a numbers or infinities to continue to execute and produce results that may be of value to the person who wrote the program. Therefore, in some situations it might be useful for you to learn more about these special forms, but in general, for many of the programs that you may write, the normalized form as well as the representation for 0 might be the only aspects of the IEEE floating point standard that you encounter. But as I had said before, also bear in mind that it may be useful for you to be able to write a program which could determine whether the hardware on which you are running the program is running using IEEE floating point standard. Right? And in order to write such a program, it may be useful for you to recap what we have said and talked about in this lecture. To write such a program, you would have to know how the IEEE floating point representation represents a value, minus 1 to the power s multiplied by 1 point f multiplied by 2 to the power e minus 127. And then you'd have to write the program in such a way that it looked at the bits inside the 32-bit float in order to determine whether the value corresponds to what it should have been under the semantics of the program. So once again, thinking of writing programs which do things on the system in order to understand more about what happens during the execution of the program. So with this, we have understood more about how real data is represented, and in short, we have understood the representation in most computer systems of the three main kinds of data: character data, signed integer data, as well as real data. Now, character data will be used to represent characters. The characters will be declared as characters. You might have arrays of characters which end up finding use as strings. Right? So a lot of what we have said may have relevance as far as string data is concerned. Remember that the real data I talked about referred to the IEEE floating point. The IEEE floating point that I talked about was the 32-bit IEEE 754 standard. You may be aware that in C programs you can also talk about double floats. For example, you could declare a variable as double x semicolon. Now that is a situation where you want to have more precision inside the representation of the real value, and that is not represented using the 32-bit IEEE 754 representation that we saw, but rather using a larger representation called the IEEE 8, which is covered by another IEEE standard. So there are representations for more precise real values as well, and that is what would happen if your program was written to use a double float or a double value. So we have not covered all the aspects of characters, integers, and real, but we have a very good understanding to start with. Okay, so with this, we are ready to move into the computer. And for the rest of this lecture, I'd like to give a quick overview of what to expect when we actually start looking at the innards of the computer. This is something which you may have seen again in school or in your undergraduate education, but it is useful to start from scratch to make sure that we are using the same terminology. So I'm going to start here with a few lectures on basic computer organization. Okay, now, as you have probably heard, there are three main parts to a computer system. One of the most important parts of the computer system is what is called the processor, or the CPU, or central processing unit. And it is the processor which essentially executes your programs. The processor which contains a lot of circuitry which is capable of executing the instructions which you have used to describe the algorithm that your program is implementing. The second main part of a computer system is something called the main memory. And basically the main memory is the circuitry of the computer system which holds the program and its data. We have seen that a program in execution is made up of many instructions, but it also manipulates data. Some of the data may have been statically allocated, some of the data may have been heap allocated, some of the data may have been stack allocated, depending on the lifetime of that data. But all of that data and all of the instructions must be present inside the computer in order for the instructions to be executed by the processor. And therefore, the main memory is a very important part of a computer, because that is where the program and its data reside when the program is executing. The third and another important part of a computer system is the different I/O devices or input and output devices that are present in the computer system. And they are important because they provide for communication between the inside of the computer and the outside world. And very clearly, in general, for the programs that you write, if you could not communicate with your program, then it's not clear what kind of objectives could be achieved. For example, if your program was multiplying matrices, it's possible that you would want to see the outcome of that multiplication and would therefore need to not just have the result of the multiplication available in memory, but also have it made available to you, possibly on a display device or printed on a printer, etc. So there are many different kinds of input and output devices. Input devices for you to interact with the computer, and output devices for information to be output from the computer. So these are the three main parts of a computer system. And when we talked about the program, I talked about the fact that a program contains a description of algorithms, initially programmed by you in a language such as C, but ultimately compiled down and present in the a.out file in the form of machine instructions. In other words, in the form of a very primitive form that the machine hardware is able to understand and execute. So a machine instruction is, what I mean by the word machine instruction is a description of a primitive operation that the machine hardware is able to execute. An example of a machine instruction might be an instruction that is capable of adding two integers. Right? So that might be an example of a machine instruction. And we expect that as part of the processor, in order to do that addition, there might be a small circuit. And if the addition is of two signed integers represented in 2's complement, then the circuit is going to be a circuit that is capable of adding signed complement, 2's complement signed integer values. Similarly, if there may be a separate instruction to add two 32-bit floating point values, and corresponding to that instruction there might be another piece of hardware, another circuit inside the processor which can do the needful as far as that instruction is concerned. So there's going to be a correspondence between the different machine instructions and the different pieces of hardware inside the processor. Okay. Now, of interest to us is not just one instruction such as the add instruction, but possibly all of the instructions that a particular processor is capable of executing. And I'll use the term instruction set to refer to the complete specification of all the instructions that a particular processor hardware was built to execute. So for example, if we were studying a particular processor manufactured by a particular manufacturer, then I might want to look at the book or the manual containing a list of all the different instructions that that processor is capable of executing, because I know that my program ultimately will get compiled into those instructions. And it might be that there are several hundred instructions, different instructions that a particular piece of hardware today is capable of executing. So as processors have become more complicated and the needs of programs have become more sophisticated, instruction sets have become more and more interesting. And of course, we won't be studying any large instruction set in detail in this course, but I'd like to go through a simple instruction set so that we get some idea about what a set of instructions in a real computer might be like. But just starting off with the pictorial understanding of what's happening. The central and most important part of the computer system, clearly, must be viewed as the processor or the CPU, because this is where the key hardware for executing instructions and various other activities is contained. Another very important part of a computer system is the main memory, because this is where the program, instructions and data reside while a program is being executed. The I/O devices are also very important, because as I said, without them you cannot interact with your program, you cannot input data, you cannot see the results of the execution of your program. Now these are the different components of the computer system, but they must obviously be connected to each other. It's not just enough to have a processor and a lot of memory and a lot of I/O devices in a box together. If they are not connected and able to interact with each other, then they cannot together cause the execution of a program. So there must be some connectivity between them, and I'm going to show that here by a central box of connectivity, which I'm just labeling as bus, and that just refers to some mechanism for connection between the different I/O devices, the memory and the CPU. So we get an idea that this is an integrated whole, and that if the instructions are initially available in the memory, they might move over the bus into the processor in order to be executed, and that if a piece of data is currently available at a particular memory location, if it is needed as the input of a particular add instruction, let's say, it may move over the bus into the processor in order to reach the adder and get added. An additional complexity which we'll learn more about later is that before my program starts executing, in other words, before I request the computer system to execute the program is not present in memory at all. Where is the program present? If I have typed the program into a file and compiled it, then both the hello.c, the C source code, source program file, as well as the executable object file a.out will be present on a disk, and a disk is an example of an I/O device. So if I have written a program and compiled it, then the a.out corresponding to my program will be present on one of the I/O devices called the hard disk. When I give a command to the computer system to execute the program, I expect that components of that a.out file get loaded into memory, into this main memory, and that from this main memory the instructions get transferred into the processor as needed in order for the program to be executed. So this integrated whole is what we have to understand, not just the processor, not just the memory, not just the I/O devices, but how they interact in order to achieve the execution of a program that I may have written. But in order to understand the interaction, we have to start by understanding the individual components. There's no other way to do that. So we are actually going to start by trying to understand each of these components one by one to a certain degree, and that's the objective of basic computer organization. Initially our interest will be on the processor. Now in your experience you would have seen that there are many different kinds of processors. For example, a lot of you have PCs, and by default there is a particular kind of processor inside a personal computer today, whereas in a college or in an institution may have come across other machines which are meant for other purposes and have different processors in them. And you'd expect that different kinds of processors may have different instruction sets, and that therefore they may have fundamentally different capabilities as far as executing programs are concerned. For example, a particular processor may have a particular instruction set and therefore will not be able to execute an a.out which has been generated for some other processor. So we must bear in mind that there are different kinds of processors. Each processor, different kinds of processors may have different instruction sets, and that they may not be compatible with each other. It is possible that some processors may be compatible with each other, but that others may not. And that in general an a.out which was created for one particular processor may not be able to execute on another processor. But it's in this course we're just going to study one particular kind of simplified version of a commonly occurring processor, so that we'll have a good understanding about what happens in most situations. But it should be clearly understood that you may have to recompile a C source program in order to make it execute on different programs. Okay, now we'll actually start looking at the more detailed composition of the processor in our next lecture. For today, let me just recap what we learned in today's lecture. We recapped our previous lecture in which we had learned about how character and signed integer data are represented. We then went ahead to look at the IEEE floating point representation for real data. We looked at it in some detail. The representation for real data is fairly important because a lot of the computation that you do in scientific or engineering applications will actually be in terms of real data. After this, we started looking a little bit at the organization of a computer and understood the basic three components. The idea that there is a processor, which is the piece of hardware which is capable of executing instructions, that there is a main memory, which is where the instructions and data of a program reside when the program is in execution, and that there are I/O devices through which interaction with the outside world happens. In our next lecture, we will look in more detail at each of these components, starting with the processor. Thank you.